The world's computing needs have grown exponentially in recent years due to an explosion of technology. To meet the needs for the next technological leap, the scientific community is working to improve current processing capabilities and simultaneously develop entirely new computing methods. Two new papers from the research group of Jean Anne Incorvia, a professor in the Cockrell School of Engineering, aim to contribute to both of these scientific needs. Together, they offer improvements on current semiconductor technology as well as a nimbler building block to the next generation of computers that think like the human brain. New research published in the journal ACS Nano relates to transistors and circuits. Within chips are components called logic gates that interpret digital signals. These logic gates are transistors that can generally conduct either electrons or holes, which occur when electrons move around within atoms, but not both. In this paper, the researchers linked logic gates together that could conduct both electrons and holes. They show that this achievement reduces the number of transistors needed in a circuit, and that means more transistors could be packed into the same space, making it both more efficient and powerful, or the saved space could be used to shrink down the device. They also demonstrate a new circuit that specifically leverages the transistor behavior. The transistors are made out of ultra-thin two-dimensional materials which have this naturally ambipolar property that allow them to conduct both holes and electrons. However, they didn't do a great job of it on their own. Refining that capability is a major component of this paper, and through their device engineering, they show important XOR, NOR and NAND circuits without needing any other devices but ambipolar transistors. These circuits are the basic building blocks of larger circuits. The researchers showed this capability at a fairly large device size. Their next steps include shrinking the devices down and further reducing the power consumption needed to make them commercially viable chip components. These findings apply to current computing technology. A second paper published recently in the journal Applied Physics Letters looks at the next generation of computers, those that think more like the human brain. These neuromorphic devices are better than traditional computers at AI tasks like interpreting images and language processing. In this new paper, the researchers created a new type of artificial neuron which in the human brain are responsible for sending information between brain cells using magnetic materials. Artificial neurons represent a popular area of neuromorphic computing research. What makes these neuron devices stand out is the chaotic nature of their reactions to electric pulses. They outperformed other artificial neurons as part of neural networks in interpreting images, specifically when the data to be interpreted was noisy. The devices fared better than other artificial neurons in identifying images of blurry shoes, and the gap widened as the blurrier the images became. Because the device itself is stochastic in its response to the input data, it performed better dealing with noisy data set. These neurons could be impactful for edge computing users where devices need to be smaller, use less power and are far removed from a central computing source like a cloud server. They are also resistant to radiation. One of the initial applications of this technology could come in outer space where silicon chips struggle to stand up to the high level of radiation. The ability to deal with radiation as well as messy data could make these neurons ideal for future space-based technology.